Right. So I'm going to talk about Majorana fermions in quantum spin liquids. Uh, and please let me know if you have any problem with my internet connection. But let me try like this. Okay, so the plan is I'm going to start with an introduction. Talking of, can you hear me well now? Just checking.
Yeah.
It's okay? Okay.
Yeah, the sound
Uh,
is good. Yeah.
all right. So I'm going to start with an introduction about fractionalization in strongly correlated systems and how that can give rise to anionic statistics. And then I'm going to gradually focus on quantum magnetism and talk about quantum spin liquids as examples of systems that can harbor anions. And the main story will be about the Kitaev spin liquid and how to use electric fields to manipulate Majorana fermions, Majorana zeromodes in Kitaev spin liquid. So, we're in condensed matter physics, we're in the business of trying to understand different phases of matter. And part of this job is to try and understand not only the ground state of a given Hamiltonian that we believe describes our system of interest, but also to understand the low energy excitations. And usually we try to organize the spectrum in terms of elementary excitations. And then when we compute correlation functions, the local operators that act on the ground state create one or more of these elementary excitations. And this is useful because, usually we're interested in understanding how the system responds to external perturbations, or we also want to talk about dynamics. So we need a simple picture for the excited states of usually unsolvable models. And some very famous examples here of how um, we think in terms of these emergent elementary particles in condensed matter physics. We can get either fermions or bosons. So for instance, in Fermi liquid theory, we have fermionic quasiparticles, which are adiabatically connected with non-interacting electrons, and in the sense that they carry the same quantum number as the electron, like the elementary charge, and also spin on half. We also have examples of bosonic excitations, for instance, bosonic collective modes that appear in broken symmetry phases, like phonons in crystals, or magnons, which are the quanta of spin waves. So we can get either fermions or bosons in this description of our interacting quantum many-body system. But what I really want to talk about are the more exotic cases where the elementary particles are really fundamentally different from the original particles or the electrons, because they carry a different set of quantum numbers, actually a fraction of the quantum numbers of the original particles. And perhaps the most famous example here is the fractional quantum Hall effect, which appears when you have a 2D electron system in the presence of a magnetic field perpendicular to the plane. And as a function of the magnetic field, what one observes is that there are some plateaus in the conductance, or the Hall conductance or Hall resistance of the system, defined here as the ratio between the transverse voltage and the current that is flowing through the system. And this Hall response is quantized in a multiple of the quantum of conductance squared over h. And in the fractional case, the coefficient here is a rational number. It's not an integer, but a rational number. And from the point of view of understanding the spectrum of this fractional quantum Hall effect, this was first discussed by Laughlin, who proposed variational wave functions both for the ground state and the excited states of the fractional quantum Hall effect. And by analyzing these variational wave functions, Laughlin showed that the elementary excitations here are, first of all, they cost a finite energy, so the fractional quantum Hall effect is a gapped or incompressible phase. and these elementary excitations in the bulk carry a fractional charge. So one way to picture this, or to realize this, is that you can think of taking the 2D electron system, which has a gap in the bulk, but then you insert locally a line of a magnetic field. It's like a very thin solenoid, and you insert a flux quantum. And you ask how the charge density of this fractional quantum Hall system varies in the vicinity of this flux. And Laughlin showed that this vortex here, or this quantized flux line, actually attracts a charge which is equal to the electron charge times the same number nu, this fractional number, which is identified with the filling factor. So for instance, in the nu equals 1/3 plateau of the quantized Hall conductance, you would trap here a charge which is equal to E/3, or a third of the electron charge. And in the bulk, these are gapped excitations, but another interesting aspect of the fractional quantum Hall effect is that if you have an open geometry, you get gapless states along the edge. And these are chiral edge states, in the sense that these are gapless one-dimensional modes that propagate in a well-defined direction that depends on the direction of the magnetic field. And these are understood in terms of Luttinger liquid theory, which again has some exotic excitations which are fundamentally different from just non-interacting electrons. And besides the fractional charge, the excitations of the fractional quantum Hall effect also have fractional statistics. And just to remind you what this means, so in usual bosonic systems, we have a wave function that is invariant under the exchange of two particles. And in a fermionic system, the wave function picks up a minus sign when we exchange any of two particles in the many-body system. But in two-dimensional systems, there are more possibilities. You can ask what happens if you trap some of these elementary excitations at fixed positions inside the system, and you take one around the other, which is like a real physical exchange process. And one can show that in this case, in the fractional quantum Hall effect, the wave function picks up a phase, theta here, which depends on the filling factor. It's going to be like pi over n for the filling factor as I defined before, which means that these particles here are neither bosons nor fermions, but they're called anyons, which is the word you use to refer to particles that have any kind of statistical phase theta here. And
just a question.
Yeah, sure.
Is there a relation between abelian anyons and parafermions?
I think it's similar in the sense that for parafermions, you also pick up this arbitrary phase, right? And yeah, I think it's fair to say that yeah, they are related.
Okay.
You're thinking in one dimension, right? The parafermions in one dimension. So here I'm going to focus on the case in two dimensions, where this theta here is just some. It's a fraction of pi, but in one dimension there are even more strange possibilities that I'm not going to talk about today. But it could be like a continuous phase. But it's yeah. So I would say there is some relation.
Okay, go on.
Okay. So this has been known for quite some time, but the experimental demonstration of fractional statistics is quite recent, from last year. So, for instance, there was this experiment where they fabricated some kind of Fabry-Perot interferometer for electrons, where one measures the conductance across the device, and the result depends on the interference between electrons that go around the loop here a certain number of times. And the result for the conductors depends on the phase that the electron picks up in this process, which you can control by applying an external magnetic field, but it also depends on the presence of quasi-particles with fractional statistics inside the loop here, which are this sort of vortex-looking things. So one can vary the gate voltage here, and then you observe that there is sometimes some slip in the phase pattern for this interference pattern, which is interpreted as a sign that some quasi-particle has been injected in the system, and this phase slip in this pattern is exactly what you would expect from the fractional statistical phase for these abelian onions. And there are even more exotic kinds of excitations. So now I'm going to start talking about Majorana zeromodes. And these are excitations that appear in a number of systems. And basically, they appear as localized Majorana fermions. They're localized at defects. And they're zeromodes in the sense that they cost zero energy. So the Majorana fermions in the sense that the operators that are associated with these particles are Hermitian. So one usually says that the particle is equal to the antiparticle. They are fermions because they anti-commute, and they are zeromodes because they commute with the Hamiltonian. So creating or not creating these particles does not change the total energy. And the index I I'm using here is because these modes, I'm going to assume they are localized at some position in space, which is usually attached to some kind of defect in one dimension or two dimensions. So for instance, even in the constant context of the fractional quantum Hall effect, there was an example of a phase that has Majorana zeromodes. This is the phase with filling factor nu equals 5/2. More recently, people have become interested in Majorana zeromodes because of some proposals that they appear in topological superconductors. So there's the famous example of the Kitaev chain, which has these two phases. One of them is topologically trivial superconductor, and the other one is non-trivial, in the sense that if you have open boundary conditions, you get these zeromodes that are localized at the edge of the chain. And these zeromodes, they appear in the middle of the spectrum. In the bulk, you have a gapped spectrum. And the zeromodes give rise to a robust degeneracy in the sense that this degeneracy cannot be lifted by any local perturbations. And we say they're topologically protected because they're really topological invariants associated with these phases that distinguish between the trivial and non-trivial phases. And you can use them to predict the presence of these Majorana zeromodes. And in two dimensions, there's the famous proposal by Fu and Kane that if you take a 3D topological insulator and have an interface with a conventional superconductor in this two-dimensional interface, you get a topologically non-trivial phase, which will have Majorana zeromodes bound to vortices that can go through the superconductor. So it's kind of similar to my discussion before about the flux quantum in the fractional quantum Hall effect. You can think that if you apply a magnetic field here through the superconductor, there'll be vortices penetrating here, and whenever there is a quantized vortex line, it will trap a zero mode, Majorana zeromode at this interface. And again, these are going to give you some robust degeneracy, and quite generally, this degeneracy will grow exponentially. Excuse me, exponentially with the number of Majorana zeromodes. This has attracted a lot of attention in the past, let's say, 20 years, since Kitaev pointed out that Majorana fermions or Majorana zeromodes are quite useful for implementing a kind of topological quantum computation which is intrinsically protected against errors. And the idea is that these Majorana zeromodes, they're also anyons in the sense of generalized statistics, but they're more exotic because if you exchange two of these particles, two Majorana zeromodes, the result is not just a phase that the many body wave function picks up at the end of the process. It's actually a unitary transformation in the subspace of this of the ground state with this fixed number of particles. Like I said, if you have a number of Majorana zeromodes, you have a degenerate subspace, which is defined by occupying or not the fermionic modes that you define from these Majorana fermions. And so if you do some kind of operation like this, bring in one Majorana zeromode around the other, the order in which you perform this operation is important, right? So the operations do not commute, and that's basically because exchanging two Majorana fermions, say I and J, acts as a unitary transformation in this degenerate subspace. And in this case, the Majorana zeromodes are sometimes called Ising anyons, because part of the story is how say you apply this kind of unitary transformation, you would also like to measure the state that you get after performing these operations to read the state of your quantum computer, and this is usually done by fusing two Majorana modes. And the fusion rules for these particles are the same as the fusion rules in Ising conformal field theory. That's where the name comes from. And since the degeneracy of the subspace is topologically protected, like I said, this is some kind of intrinsically fault-tolerant quantum computation. So this has been pursued as a possible route for a quantum computer by a number of groups. And Microsoft has invested a lot of money in this kind of idea, and there are already experiments that try to detect the signatures of Majorana zeromodes in realizations of this Kitaev chain in quantum wires with some proximity-induced superconductivity. And there are already proposals for, say, if we convince ourselves that the Majorana modes are really there, how would you go about braiding Majorana zeromodes at the ends of this quantum wire? So there's this kind of proposal here with T junctions. There have been some missteps along the way. You probably heard about this paper that was retracted, I think it was a few months ago, because it was originally interpreted as a sign or evidence for Majorana zeromodes in quantum wires, but at the end, they could not really rule out alternative explanations. But the search is still going on, and the kind of system that I want to tell you about that can support Majorana zeromodes is not this kind, but I want to offer an alternative, which is in a quite different setup in terms of insulating systems that are quantum spin liquids. So now I'm going to switch to talking about quantum spin liquids. And okay, so let me give some vague definition here of what a quantum spin liquid is. So I'm going to use this word to refer to Mott insulators. So these are systems in which the electrons do not move around because of strong on-site repulsion. And so you can think that they're only localized electrons, and what matters are the local magnetic moments of these electrons. So I'm just going to represent them by local spin operators, which are distributed on this lattice. And they're quantum spin liquids in the sense that the ground state of the interacting spin system does not order magnetically, does not develop long-range order, even at zero temperature. And when it does that, it has to be because of quantum fluctuations, some kind of frustration mechanism that prevents long-range order. And the interesting thing is what happens when the system manages to avoid long-range order. And since Anderson's proposal back in the 70s, we know that such a ground state of quantum spin liquid has to be highly entangled, what Anderson called a resonating valence bond state. And that's usually represented by this kind of picture here. So one way to construct a ground state that does not break spin rotational symmetry is to write down this kind of superposition of singlets. So say you take two sides and write down the singlet wave functions for the spins that live on those two sides, and you write down this superposition, and then it's it's going to be naturally invariant under spin rotations, and because of the superposition, it's also invariant under lattice rotations, and it preserves all the symmetries of the original Hamiltonian. Moreover, if you consider excitations on top of such a ground state, these excitations are going to be fractional, and these are what we call spinons in this context. So one way to excite a system like this is to break up a singlet by turning the singlet into a spin triplet, for instance, like here. And in a cartoonish representation, you can think that I can take these two spins up now, and in this complicated superposition, these two arrows are going to be separated by arbitrary distances. So this excited state is actually understood in terms of two independent or deconfined spins 1/2 that are created on top of this RVB state. And they're fractional, just like in my original definition at the beginning of the talk, in the sense that the excitations or the excited states of the system always carry integer spin. Say if I start with a singlet, my low-lying excited states can be triplets, for instance, but this total spin 1 of the excited state is actually split between two spins 1/2. And there are many kinds of quantum spin liquids. For the purpose of what I want to talk about, and the most interesting ones will be chirospin liquids. The word chiro here refers to the fact that these phases actually do break a symmetry, which is a reflection symmetry, and moreover, they break time reversal symmetry. And the first chirospin liquid to be proposed was the Kalmar-Laughlin state back in the 80s. Basically because, I guess, Laughlin realized that in the same way that he could write down a wave function for the electrons in the fractional quantum Hall effect, you could take a spin system where it represents spin operators in terms of bosons, as in Hostin-Primakov representation, and write down a wave function for those bosons that would be a state that does not break spin rotational symmetry. And it turns out it's equivalent to a fractional quantum Hall effect of bosons at filling factor nu equals 1/2. And so in this case, one can show that the excitations of the Kalmar-Laughlin states, they're also spinons, and they're abelian anyons. They're actually called semions because the statistical phase is half of the electron, so of fermions. Because for fermions, you get a minus sign, right? So it's like e to the I pi for the statistical phase. Here it's pi over 2. And more recently, there have been some proposals and actual numerical evidence that the Kalmar-Laughlin state is stabilized in some not too complicated Hamiltonians. For instance, this one on the Kagome lattice that has Heisenberg exchange interaction between nearest neighbors, and this type of three-spin interaction on all triangles here of the Kagome lattice. So this kind of interaction is important because it gives a sense of chirality, right? So this is already the scalar spin chirality for these three sides. And then it induces this kind of phase that has a sense of circulation for spin excitations, which in a simple picture is very much like a fractional quantum Hall effect. It has an energy gap in the bulk and edge stages that are gapless and chiral. So they circulate in a given direction, and these are edge states of spin excitations. They can carry spin and can carry energy. And the main example of a quantum spin liquid that I want to describe now is this Kitaev spin liquid. It was introduced by Kitaev in 2006 as a model on the honeycomb lattice. It's defined by this Hamiltonian that has only nearest neighbor interactions on the honeycomb lattice, but the interactions depend on the direction of the bond. So let me try to explain this. So you basically have to take the honeycomb lattice and divide the bonds into 3 sets. So each site has 3 nearest neighbors, and you label the bonds by X, Y, and Z. And then for the nearest neighbor bonds on the X direction, you take the Ising-like interaction with the X component of the Pauli spin operator. And you do the same for Y and Z. So this is a kind of interaction which has some frustration built in because of the spatial dependence of the exchange interaction. Kitaev proposed this model because he later he showed in this very same paper that this model, even though it looks complicated at first, it's a model of interacting spins on half in 2 dimensions. It's actually exactly solvable by a Majorana fermion representation of spin on half operators. And the representation is this one that I wrote down here. So for each site, you have to consider that you're going to break up the spin on half operator in terms of 4 Majorana fermions. So these obey the algebra that I showed before. And there are 3 types of B's. So there's like the X component, you take Px times C. So there are 3 types of B Majorana fermions and 1 C Majorana fermion. And when you plug this into the Kitaev model, into this Hamiltonian, it's actually convenient because you can take 2 B Majorana fermions from neighboring sites. Let me choose here, say the Z bond. And then I take the B Majorana fermion from this side with the B from the other side. I can define these operators with a factor of I, the operators I'm going to call U. These are defined on the bonds. And these are gauge variables in the sense that these are variables that are defined on the link. And they actually, something I should have said before, so let me go back here. This representation actually has a gauge structure because if I write the spin operator like this, there's a gauge transformation that I can do where I change the sign of both of all fermions at the same site, but this does not change the physical spin operator. So this kind of representation is actually defined in a bigger Hilbert space, and to make sense of it, we need to impose some local constraints. So what you end up with some kind of gauge theory on the lattice, where these are now the gauge variables that live on the bonds. They are defined from these B fermions, and remember we still have the C fermions, which are the yellow ones I'm representing here in the middle of the site. And these U's are not gauge invariant, but you can define product of U's around closed loops, very much like we do when we define the magnetic flux in usual electromagnetic gauge theory, right? You take the integral, the line integral of the vector partition around a closed loop. That's the magnetic flux. So I can multiply all the U's around a loop here. The smallest loop is a single hexagon. So this gives us a gauge invariant plaquette operator, which I'm going to call a flux operator. And the interesting property of the Kitaev model is that these plaquette operators are conserved. They commute with the Hamiltonian for every single plaquette. So this is a model that has a macroscopic number of conserved quantities, and you can use this to solve the model exactly. So what happens then is that since these are conserved operators, they're actually Ising operators. They square to 1, so the eigenvalues are plus or minus 1. You can fix a given sector with all the eigenvalues equals to plus 1. So this removes the B fermions from the story, and all that you are left with are the C Majorana fermions that can move freely on the background with a fixed flux configuration. So basically, the solution is that you manage to map a problem of interacting spins on half onto a model of non-interacting Majorana fermions. And what I described so far was the Kitaev model in the absence of a magnetic field. And in that case, the spectrum is basically a Majorana fermion hopping on the honeycomb lattice. So the spectrum is very similar to what we know from graphene. There is a Dirac point at the K point of the Brillouin zone. But it's also interesting to see what happens when we add an external magnetic field. And Kitaev also considered this problem. He showed that if you treat the magnetic field perturbatively, the magnetic field, by breaking time reversal symmetry, gives rise to a non-trivial, topologically non-trivial mass for the Dirac or the Majorana fermions in this case. So what you get is a topological phase of this C fermions, which has a non-trivial Chern number. and which is very similar actually to how they model on the honeycomb lattice. And since this is a phase that appears when you add a magnetic field and break time reversal, this Kitaev spin liquid in the magnetic field is actually a chiral spin liquid as well. It's a chiral non-abelian spin liquid because you can show that it supports Majorana zeromodes. So let me just point out here that the excitations in this case are, well, first we have the C fermions that are moving in the background of this flux configuration, but it will also have the possibility of changing the eigenvalue of these plaquette operators. Like I said, the ground state is in the sector where all the WPs are equal to plus 1, but if you change one single eigenvalue here, it's like changing the flux from 0 to pi, say. So I'm going to call this a vortex excitation of this emergent gauge field that appeared from the B fermions that we used to represent spin operators. Okay, so there are two types of excitations, the C Majorana fermions and these vortex excitations. And what happens in this gapped phase in the presence of the magnetic field is that vortices bind Majorana zero mode. So there will be localized wave functions around defects of this flux configuration. And this is why this is also a non-abelian spin liquid phase. And then it turned out that Kitaev's proposal of this exactly solvable Hamiltonian was relevant for experiments because Giacelli and Caliuli showed in 2009 that the Kitaev interactions appear naturally in some Mott insulators with strong spin-orbit coupling. And some examples here are the iridates, and the compound I'm going to focus on is ruthenium trichloride, which is illustrated here. So the important point is that the ruthenium ions form a honeycomb lattice, and if you take into consideration that ruthenium 3 plus has an electronic configuration that has a single hole in the set of T2D orbitals. So there are some important ingredients here. So first is orbital degeneracy, spin orbit coupling, and also taking into account that this is a strongly correlated system. It's going to be a Mott insulator. What you end up with is a Mott insulator that is described by an effective spin model, which has angular momentum. Here is total angular momentum because of spin orbit coupling. J equals a half. So for all purposes, it's a spin on half model that has as the dominant interaction the Kitaev interaction that I wrote down before. And a couple of years ago, there was some evidence actually that Majorana fermions might be present in ruthenium trichloride. And the evidence came from this transport experiment that measured the thermal Hall conductance. So it's very similar to the charge conductance that people measure in the fractional quantum Hall systems. But here we're talking about heat transport. Remember, this is an insulator, but you still have some excitation that can carry energy. And what they saw is that if you take ruthenium trichloride in the presence of a magnetic field, first at low fields, the system is actually in a magnetically ordered phase because of perturbations that take you away from the Kitaev spin liquid phase. But then at some point, this magnetic order is suppressed by the field, and you enter this intermediate regime here, where the thermal Hall conductance is observed to take on this quantized value, which in the proper units is exactly 1/2. So there's like a plateau here. And this is evidence that actually there could be a chiral Majorana fermion at the edge. So as predicted from the Kitaev model. So remember, we have Majorana zeromodes as excitations in the bulk, but if you have an open geometry, you can have gapless Majorana modes propagating along the edge, and then this can transport energy ballistically and give rise to quantized conductance. How am I doing with time? Because I started late, so.
You can go ahead. Just have 15 more minutes.
Okay, great. Thank you.
Sure.
Okay, so this is still being debated whether this interpretation of the experiment is really concrete evidence for Majorana fermions. But of course, we would like to have more evidence coming from different kinds of experiments. So we started thinking about alternatives here, and also an interesting question is, suppose there are Majorana fermions in ruthenium trichloride, how would you go about moving them around so you can perform this kind of exchange process that you want to have for implementing topological quantum computation, right? So you'd like to manipulate them somehow. And the story I want to tell you is that we actually show that this can be done with electric fields, which at first may sound strange because we're talking about electric fields in a Mott insulator, and normally one thinks that the Mott insulator will respond to magnetic fields because there are spins, but not to electric fields. But it's a little known fact, I think, that Mott insulators actually have, or they may have, non-trivial electron polarization response. And the principle is actually quite simple. It's basically because you have to think that the low energy subspace of the Mott insulator is understood in terms of spin operators, but in general, all kinds of operators, you have some representation in this low energy subspace. This is what we do or what we take into account when we derive, for instance, the Heisenberg interaction from perturbation theory in the hopping process, right? So to get an antiferromagnetic exchange interaction, you have to consider that the electrons in the Mott insulator will hop to a nearest neighbor site and then discuss some finite energy U, but then it hops back into another state in the low energy subspace, and you generate an effective Hamiltonian in the low energy subspace. And in principle, you should do this for every kind of operator, including the charge density operator, which counts the number of electrons at each site. The difference here is that to get a non-zero representation for the charge density operator in the low energy subspace, you have to go to higher orders in perturbation theory, which one can do by applying some kind of a Schrieffer-Wolff transformation. It can be done systematically. And the result here, which were discussed by these guys for general Mott insulators, is that the fluctuation of the charge density away from 1 will be given here in terms of this operator, which is written in terms of spin operators, but the process is generated at third order in perturbation theory. So it's something like the electron that it's initially at site I, it has to hop to site 2, 3, and then back to see that there's some kind of spatial inhomogeneity among the sites. So it may be more convenient for the electron to sit at one given site as compared to the others. And this is determined by this result here. At the end, the charge density at site J depends on summing over triangles that site J forms with other sites K and L, and it will depend on the spin correlations like this. So for instance, here in this case, the charge density at site 1 may be, let me try to get the sign right, it may be lower if this is a strong bond, say this is K and L in this notation. So if this spin correlation is stronger between these two sites than the other sites, then this expectation value here will be non-zero. So this will generate a non-zero charge density here at site 1. And then you can get some electric dipole moment pointing towards that site. So what we did was to apply this idea to the model for ruthenium trichloride. It's a bit more complicated than the Hubbard model. It's what's called a Hubbard-Kanamori model because it includes orbital degeneracy. Remember, there are 3 T2D orbitals, which we have to discuss or describe here in terms of an effective orbital angular momentum operator. And there are all these terms in the atomic Hamiltonian. Moreover, the hopping processes are orbital dependent. And this was as analyzed originally by Jacquelli and Khalil. So basically what you have to do is to consider this kind of a third order perturbation theory process in which electrons hop around triangles in the honeycomb lattice. And here we have to include second neighbor hopping to close the triangle. But at the end, the idea is very similar, and we can obtain an expression for the local charge density in terms of spin correlations, which we can then compute exactly for the Kitaev model because it's exactly solvable. So we do this by basically we want to consider how the correlation functions, the spin correlation functions, are modified in the presence of a vortex that will trap the Majorana Zeromode. So we compute correlations as illustrated here for bonds that are right next to the hexagon where the vortex sits, and we put the vortices at the largest possible distance for a finite system with periodic boundary conditions. So say some geometry like this, and then you put 2 vortices at some distance here, L/2, if L is the system size. And this is just to show that the result converges to a finite value when you take the thermodynamic limit. So and then you just have to plug this result for the correlation functions into the expression for the charge density operator to compute the charge imbalance around the vortex. And this is the result. And so here I'm showing this expectation value of the charge density, I'm calling it rho J, around the vortex, which is this gray hexagon. And red color here represents negative charge and blue is positive charge. So you can see that if I have a Z2 vortex somewhere in this Kitaev spin liquid, it will generate some oscillating charge density, which is kind of like Friedel oscillations in a normal metal, but here it happens in a Mott insulator. And since there is this charge distribution here in sort of rings that oscillate with positive and negative charge, and also decay with distance, this will generate an intrinsic electric field, which in terms of the electric potential as a function of the distance from the plane of the material, this is a quadrupolar-like field that decays with one, or quadrupolar-like potential that decays as 1 over distance to the cube. And when you plug in some numbers, estimates for the parameters in ruthenium trichloride, we come up with this estimate that for the order of magnitude of the electric potentials we're talking about here, it's a fraction of a millivolt, which is quite small, but it's still detectable by state-of-the-art atomic force microscopy. So this is one way we propose how one might be able to detect vortices and Majorana and the associated Majorana zero modes by measuring electric fields on a single layer of ruthenium trichloride. But besides intrinsic detection, we also can look at what happens when you apply an external electric potential and whether it likes to attract these vortices, and that is indeed the case, because we can include a local potential V0 in the atomic Hamiltonian, and then we do this calculation of the effective spin Hamiltonian, and it turns out that this a non-zero local electric potential attracts vortices because the energy of the vortex goes down as a function of V0. And this could be useful to trap and move these Majorana zero modes, which are located at the vortices, because here you could have a scheme with several tips, say 4, and then if the vortices are trapped at one of these, you can move them slowly and then carry one around the other to perform this kind of exchange operation. And moreover, you can also use these external fields to detect the spectrum, the excitation spectrum. It's also a possible kind of a spectroscopic detection of Majorana zero modes. So the calculation here is this standard time-dependent perturbation theory. Say in this kind of geometry, you have 4 STM tips, and then you apply an oscillating field to one of these, and you ask how the system absorbs energy from this AC field. And the answer depends on whether there are vortices at the tips or not. Here I'm showing the case in which there are 4 vortices located at the tips. And here's the absorption spectrum for when there is no vortex, 2 vortices, or 4 vortices. And the important point is that this alternating field will couple to the effective charge operator, which is written in terms of 2 spin operators. So this can excite Majorana fermions in the spin liquid. And the most interesting case is when there are 4 vortices at the tips. You see that there is a peak here at very low frequencies when I bring the vortices close together, and this low energy peak is actually a signature of this Majorana zero mode, which actually moves to finite frequency if you bring the vortices close together. So this could be an interesting way to search for evidence of Majorana zero modes in Kitaev spin liquids. And with that, I will conclude. So I told you about quantum spin liquids. These are interesting phases with all kinds of excitations with fractional statistics. Some of them can be abelian anyons or non-abelian anyons. The one I focused on was the Kitaev spin liquid, for which people believe there is an experimental realization in ruthenium trichloride. And I told you it's possible in principle to manipulate vortices in the Kitaev spin liquid, and these vortices trap Majorana zero modes using electric potentials, because the vortices modify the spin correlations and the vortex energy, and this might be useful to manipulate electrically. So thank you, and again, sorry for the technical difficulties at the beginning.
Thank you, Rodrigo. Rodrigo, for a very nice seminar. It was not your fault. This is clear. The platform had a problem today. So questions? Does anyone have questions? I have one. You showed when you showed the STM tips. Is this material this material is 3D, right? It's not a two-dimensional material. It's 3D, but it's layered like the cuprates.
Exactly. It's actually the layers are weakly coupled. It's similar to, it's very much like graphene, that you can actually fabricate single layers by, like, it can be exfoliated. That has been done actually. It's with Scotch tape. Yeah. Okay. So, but most of the experiments like this, the thermal transport experiment I mentioned, it was in the 3D sample.
Which the 3D sample, okay.
Weakly coupled layer.
Okay. So that's like the cuprates and the rutheniates, I believe, where you can write an effective model that's 2D.
Yes, okay. Exactly.
Okay. Any other questions?
Yeah, I do have one question. Rodrigo, nice talk, by the way. Thank you very much.
Thank you.
My question is pretty naive. When you map your model into this Majorana fermion, when you have, you said there is a Majorana bound at the core reticle where they have the flux, right?
Yes.
So this one Majorana model. So do you find another one at the I'll say outermost border of the system? They are probably the other one is probably not local, but they probably they move around.
Because they must come in pairs, right?
Right. So since you have a finite system, probably you find the other one. You can detect it somehow.
Yeah. So the geometry we considered had periodic boundary conditions like a torus.
Oh, I see.
You can control where they are because you also create vortices in pairs actually. That's imposed by parity constraints actually. If you apply any local spin operator, you already create two vortices next to each other, and then you can try and separate them. But they always come in pairs. So you have one Majorana zero mode at each of these vortices.
All right. Thank you.
Yeah.
There is a question here in the chat from Luis Enrique. Can you comment about fractional excitations in multi-channel condo problems? I know that you worked on condo too.
Yeah. Yeah. I don't think I can say anything very inspired about that right now. I know people have, well, of course, the two-channel condo problem is an example where you do find Majorana fermions in the solution, right? And it comes from this also kind of exotic non-fermi liquid low energy fixed point. And if you go to the multi-channel condo problem, you also find all kinds of parafermions and fractional particle excitations with fractional statistics. I think there were some proposals actually to realize or to consider multi-channel condo systems as platforms for manipulating Majorana zero modes. Also has some interesting alternatives. It's not obvious you can do that because usually you want a gapped system, right? And when you can have this Majorana fermions very isolated and carry them, transport them adiabatically. But also, I think, and I'm not going to recall the details now, but if you have some, to get the multi-channel condo problem, you need to have some metallic lead coupled to some quantum dot, right? But somehow there have been some proposals where I could actually use that, manipulate the Majorana fermion at the two-channel condo fixed point as to do this kind of grading process as well.
I understand that the realization of the two-channel condo experimentally is very, very difficult. Haber Gordon did that many years ago, but he had to go to almost microkelvin temperatures to be able to do the measurements and prove that he was
Exactly.
seeing the two-channel condo problem.
Right.
So
Yeah, part of the issue is also that the fixed point is unstable, right? So it requires fine tuning.
mhm.
So you have to tune the gauge voltage, or gauge voltages, or the couplings are exactly the same, and then you have to go to very low temperatures to see the power laws with the exponents that are predicted for the non-fermi liquid fixed point.
I recall that I met him at a conference, and he said that he was trying for 1 year basically to get the results to convince the referees of the. He finally published on Nature, I think, or Science, I don't recall. But it shows that it's not easy. It's not an easy setup to realize.
Right.
I have another question. When you showed the calculations you did a little bit before that, 2 slides maybe before that. No.
Let me just add something about the two-channel condo problem that I actually just remembered.
Sure.
There is a connection, because if you're interested, you can go to this paper, this one that I cite here about the Cagomeleres, and the way they originally understood this Chirospin liquid is in terms of a two-channel condo problem. They have this picture, like the arrows at each side. It looks like there is one arrow coming into. How do you do this? One arrow coming in and going out, and then there's another one, right? So somehow this has some connection with some spin modes that are coming in to this site, single site. It's like a very sharp wire, but it's going into this site, and the way they had this heuristic picture for the Chirospin liquid phase in terms of the two-channel condo effect. Yeah, I just remembered. Sorry.
Okay, no problem. Sure. You showed a calculation where you kind of did a finite size scaling. You did the different.
Yes.
This one, yeah.
Yes.
Was that was numerical, right?
Yes.
A numerical calculation. Yeah. But I understood that the problem has an exact solution. So why did you have to do numerical?
Yeah, it depends on what you mean by exact solution.
Well, okay.
I mean, you map to free fermions, but the problem is in the presence of vortices, you don't have translational invariant.
Okay.
And then you end up having to diagonalize this.
Then you have to do. You can only do numerical. Yeah. Okay.
At the end, is reduced to this kind of calculation.
Okay.
It's not any serious numeric.
Any more questions? Anyone?
I mean,
I have.
Eduardo.
Go ahead, Eduardo.
Okay, thank you, Rodrigo. I just have a curiosity about this link to the charge fluctuations in the multi-insulator with the spins that you get at higher order. I noticed that you mentioned some old references for that. So I was curious whether this has been explored in, usual multi-insulators with not with order, antiferromagnetic order or anything. If it had some impact in that case as well.
Right.
Just curious.
So it's actually kind of surprising that this is not better known. Daniel Komsky has been going around and advertising this kind of effect. What they did was to apply this to magnetic systems with magnetic order but non-coplanar order, because then you have some complicated magnetic texture which can end up inducing electric polarization.
I see.
We discussed this for some pyrochlore systems, I think. But nobody had done this for spin liquids. That's what we tried to do. But,
Okay. I was just curious about it. Thank you.
yeah.
Hey, Edson, you have a question?
Yeah, I was trying to understand a little bit better the answer to your question about this finite system. You need a finite system because you no longer have translation symmetry, right? So,
Yeah.
but it's effectively non-interacting, right? So
Yes,
presumably you could apply some sort of recursive Green function and still get larger system. What is the limitation? I mean, because now you could separate part of the system where you have the vortex, and then the rest you could suppose you have just two vortices, for instance, right? So and then
yes.
you can solve the rest recursively, and you could go longer to longer system or larger system if you wish.
Right. You probably know more tricks than I do, and
No, I'm not sure. Maybe I'm missing something here.
but here to see what we wanted to see, we didn't really need very large systems. I think the largest I consider was like 50 by 50 unit cells, and the one I'm showing here is actually smaller. You can see it has already converged.
So it's good enough.
But yeah. But there are probably some cases where you can do better.
This is just some technicality, let's say. But if it
Yeah.
isn't good enough, so you don't need any additional tricks.
Yeah.
All right, thank you.
Okay, any more questions? Anyone? The students, any written questions? I see that no, there are no questions. So we should thank the speaker again. Thank you very much, Rodrigo, for the talk. Unfortunately, we won't post your talk on our YouTube channel because we were not able to record. But I still want your slides, so we're gonna put the slides there, so anyone who wants to get the slides can download from there.
So you can invite him again to give
We
another
can
talk
invite
so
him
he can
again.
record.
Yeah, and maybe we sort out this problem with the platform. Oh, you did? Okay, so great. So we have everything we need. So maybe we should consider moving to Google Meet. This is Google Meet, right, or Zoom? I am not sure. This is Zoom, right?
No, it's a Google Meet.
This is Google Meet. Yeah.
Google Meet.
Well, so maybe we should consider moving to Google Meet, and but then we have. Vilas, why were you able to record? Because you pay for Google Meet, or because we were not able to record? 3D computer. Okay.
I learned that
Okay.
there are some extensions on Google Chrome you can record.
Okay.
Yeah.
Well. We're gonna know soon. Okay. Thank you very much.
Thank you, Xavier, for providing us the link.
Yeah, thank you for the quick thinking. Thank you.
Ô, Rodrigo, só falar com você depois, rapidinho, hein?
Tchau.
Okay, so-
Obrigado, Rodrigo.
Tchau, Eduardo.
Graças.
Tchau.
Todo mundo foi vacinado aí, Edu? Dudu?
Sim, primeira dose.
Ah, então